the silence of Mars feels wrong. Every crater, every canyon, every frozen plain seems to be hiding the aftermath of a crime so ancient that no witness survived to tell the story. This is not just another lifeless world drifting through space. Mars carries scars unlike any other planet in our solar system, scars that have forced scientists to ask an unsettling question. How does a planet that once possessed rivers, lakes, oceans, a thick atmosphere, and perhaps even the ingredients for life become the frozen desert we see today? Something happened here, something powerful enough to transform an entire world. Billions of years later, orbiters, landers, and rovers continue uncovering clues buried beneath Martian dust, each discovery making the mystery even deeper instead of solving it. Every photograph, every rock sample, every trace of vanished water points toward a planetary catastrophe whose fingerprints are still visible from orbit. Mars didn't simply change. It was changed, and the evidence is waiting to be uncovered. You're watching Starsky Science, where the universe reveals its greatest secrets. Subscribe now and join the journey. Mars has fascinated humanity for thousands of years. Ancient civilizations watched its blood-red glow cross the night sky and connected it with war, destruction, and divine power. The Babylonians associated it with Nergal, the god of plague and conflict. The Romans named it after Mars, their god of war. Even without telescopes, people sensed there was something unusual about this wandering red light. Centuries later, telescopes replaced myths with observations. Astronomers discovered polar ice caps that grew and shrank with the seasons. Dark markings appeared to shift across its surface. During the 19th century, some observers even believed they saw enormous canals stretching across the planet. Although those canals turned out to be an optical illusion, they fueled one of history's greatest scientific debates. Could Mars be home to intelligent life? As spacecraft finally reached the red planet in the 20th century, reality proved both harsher and more intriguing than anyone expected. Instead of cities or civilizations, cameras revealed a barren landscape covered in dust, broken rock, and impact craters. Yet hidden within that desolation were impossible features that refused to fit the picture of a dead, uneventful world. One discovery stood above them all. Mars possesses the largest volcano in the solar system. Olympus Mons towers nearly 22 kilometers above the surrounding plains. Its base stretches hundreds of kilometers across, dwarfing anything found on Earth. Standing near its summit, if it were possible, the curvature of Mars itself would disappear beneath the horizon. The volcano is so enormous that an observer on its slopes would never see the entire mountain. But Olympus Mons was only the beginning. Nearby lies the Tharsis region, home to several other giant volcanoes. Together, they form one of the most extraordinary volcanic provinces known anywhere in our planetary neighborhood. Their immense size immediately raised another question. Why are Martian volcanoes so much larger than Earth's? The answer begins with a crucial difference between the two planets. Earth's surface is divided into massive tectonic plates that slowly drift across the mantle beneath them. Hotspots producing volcanoes remain relatively fixed while the plates move overhead. Instead of creating one enormous volcano, Earth's moving crust builds chains of smaller ones, like the Hawaiian Islands. Mars appears to have lacked active plate tectonics for most of its history. Without moving plates, volcanic hotspots remained in one location for millions of years, allowing lava to erupt repeatedly through the same opening. Layer upon layer accumulated until mountains reached astonishing heights. At first glance, this seemed like a satisfying explanation. Then scientists looked elsewhere. Far beyond the towering volcanoes stretched something even more astonishing. A canyon system so vast, it makes Earth's Grand Canyon appear almost insignificant. Valles Marineris slices across Mars for more than 4,000 kilometers. In places, it reaches 7 kilometers deep and hundreds of kilometers wide. If placed across the United States, it would extend from coast to coast. No river carved this immense scar. Instead, researchers believe the crust itself fractured as enormous forces reshaped the planet from within. The nearby Tharsis volcanic region may have swollen upward, stretching Mars' surface until it cracked apart like drying mud. Already, Mars was revealing a violent geological past. Yet none of these features explain the greatest mystery. Because volcanoes and canyons do not kill planets, something else had happened. Orbiters soon uncovered ancient valleys branching across the landscape like dried veins. Their shapes looked remarkably familiar because similar patterns exist all over Earth, wherever rivers have flowed for millions of years. These valleys could not have formed without liquid water. Then came even stronger evidence. Spacecraft photographed rounded pebbles inside ancient riverbeds. Minerals that only form in the presence of long-lasting water appeared across the surface. Sedimentary layers hinted at lakes that once endured for thousands, perhaps millions, of years. Mars had not always been frozen. It had once been wet. Very wet. NASA's Curiosity Rover later explored Gale Crater and discovered rocks deposited by calm streams. Their smooth surfaces and rounded shapes resembled stones collected from riverbanks here on Earth. Meanwhile, the Perseverance rover landed inside Jezero Crater because scientists believe it once contained a vast lake fed by an ancient river delta. From orbit, the branching sediments looked almost identical to river deltas found on Earth today. The evidence became impossible to ignore. Billions of years ago, water flowed across Mars. Not just briefly, not occasionally, repeatedly. Some researchers believe enormous oceans may have covered much of the northern hemisphere. Shoreline-like features appear along ancient terrain, although their interpretation remains debated among planetary scientists. Even the atmosphere tells part of the story. Today's Martian atmosphere is astonishingly thin, less than 1% the pressure of Earth's sea-level atmosphere. Liquid water cannot remain stable on the surface for long because the pressure is simply too low. Ice often transforms directly into vapor without becoming liquid at all. Yet rivers require a thicker atmosphere. Lakes require warmth. Oceans require climate stability. Somehow, Mars once possessed conditions dramatically different from those we observe today. Which raises a disturbing question. Where did everything go? Where did the atmosphere disappear? Where did the oceans vanish? Where did the warmth escape? Scientists once assumed the answers might be relatively simple. Perhaps Mars was always destined to cool because it is only about half Earth's diameter. Smaller planets lose internal heat more quickly. As their interiors cool, volcanic activity declines, geological recycling slows, and magnetic fields can weaken. That explanation sounded reasonable, until spacecraft began measuring something invisible. Something that protects every living creature on Earth, every single second. Our planet is surrounded by a magnetic field generated deep inside its molten outer core. Although invisible, this magnetic shield performs an extraordinary task. It deflects much of the relentless stream of charged particles flowing outward from the sun. This stream is known as the solar wind. Traveling at hundreds of kilometers per second, solar wind constantly bombards every planet in the solar system. Without protection, those energetic particles can gradually erode an atmosphere molecule by molecule. Earth survives because its magnetic field redirects much of that assault. Mars does not. Modern measurements show that Mars lacks a global magnetic field today. Only isolated patches of magnetized crust remain, preserving faint echoes of a shield that disappeared billions of years ago. Suddenly, everything became far more interesting. If Mars once possessed a strong magnetic field, then something caused it to collapse. And if that shield vanished, the atmosphere would have become increasingly vulnerable to the solar wind. For decades, this idea remained difficult to test. Then NASA launched one of its most important Martian missions, MAVEN. The Mars Atmosphere and Volatile Evolution mission entered orbit in 2014 with one central objective: determine how Mars lost its atmosphere. Its findings transformed our understanding of planetary evolution. MAVEN detected the solar wind actively stripping gases away from Mars even today. During periods of intense solar activity, atmospheric escape increases dramatically as charged particles slam into the upper atmosphere. The process is slow by human standards, but planets measure time differently. Over billions of years, even a tiny leak can empty an ocean-sized reservoir of air. Piece by piece, atom by atom, Mars was losing its sky. Yet another mystery remained. Why did its magnetic field disappear in the first place? Deep inside, every rocky planet lies a hidden engine. Earth's molten iron outer core circulates through convection, driven by heat escaping from the interior. Combined with planetary rotation, these flowing metals generate the magnetic field surrounding our world. Scientists call this process the geodynamo. Evidence suggests Mars also possessed such a dynamo early in its history. Then it stopped. Exactly why remains one of planetary science's greatest unanswered questions. Some researchers argue the small planet simply cooled too quickly. As heat escaped, convection weakened until the magnetic engine shut down forever. Others suspect colossal impacts altered the interior in ways we still do not fully understand. Either way, the consequences would have been catastrophic. Without its invisible shield, Mars stood exposed before the Sun. And the longest planetary execution in solar system history may have quietly begun. As the magnetic shield faded, Mars did not collapse overnight. There was no single explosion, no planet-shattering impact that instantly turned blue skies into endless deserts. Instead, the transformation unfolded over hundreds of millions of years, a pace almost impossible for the human mind to grasp. Yet when compressed into the language of planetary history, it was startlingly swift. A world that may once have supported rivers, rainfall, and perhaps even primitive life slowly became incapable of protecting itself from the relentless violence of space. The solar wind never stopped. Every second, charged particles streamed outward from the Sun at speeds exceeding 1,000,000 kilometers per hour. Earth experiences this same cosmic storm every day, but our magnetic field acts like a giant invisible umbrella, diverting most of the assault around the planet. Mars, stripped of that protection, stood directly in its path. The atmosphere became the battlefield. Each collision between energetic particles and atmospheric molecules transferred a tiny amount of energy. One collision meant almost nothing. 1,000,000,000,000 collisions barely mattered. But over billions of years, those tiny losses accumulated into a planetary catastrophe. Molecules that had once been trapped by gravity gained enough energy to escape into space forever. Hydrogen disappeared first. Because hydrogen is the lightest element in the universe, it escapes more easily than heavier gases. That mattered because every water molecule is made of 2 hydrogen atoms bonded to 1 oxygen atom. As ultraviolet sunlight split water vapor apart high above the atmosphere, hydrogen drifted away into space. It never came back. The oxygen left behind faced a different fate. Some escaped as well, while much of it reacted chemically with iron-rich rocks covering the surface. That reaction left behind one of Mars' most recognizable features. Its color. The red planet is red because its surface is coated with iron oxides, the same family of compounds we simply call rust here on Earth. Every dust storm lifts billions of tiny rust-colored particles into the atmosphere before they slowly settle again across the landscape. In a sense, Mars is covered in the remains of countless chemical reactions that unfolded over billions of years. The entire planet looks oxidized, almost weathered, almost aged. Yet beneath that familiar red, dust lies evidence that Mars was once astonishingly different. NASA's orbiters have mapped vast deposits of clay minerals scattered across ancient terrains. These aren't ordinary rocks. Clays require long-term interaction with liquid water to form. They preserve chemical fingerprints of environments that remained wet for extended periods. Some formed nearly 4 billion years ago. That was during an era when both Earth and Mars looked nothing like they do today. Our own planet was still young, its continents barely recognizable. Life, if it had already emerged, consisted only of microscopic organisms hidden within oceans. Meanwhile, Mars may have possessed lakes stretching across craters, rivers carving valleys through volcanic plains, and groundwater circulating beneath its surface. From orbit, many of those valleys resemble drainage systems seen on Earth after heavy rainfall. They branch naturally, merging into larger channels exactly as rivers do across our own continents. Water shaped this world. But where did all that water ultimately go? At first, scientists believed most of it simply escaped into space alongside the atmosphere. The reality appears more complicated. A significant portion certainly vanished beyond Mars forever. Hydrogen escaping into space carried part of the planet's water inventory with it. Yet recent studies suggest much of the missing water never actually left. Instead, it became trapped, locked forever inside the rocks themselves. When volcanic minerals interact with water, they can transform into hydrated minerals, chemically storing water within their crystal structures. Rather than existing as oceans or ice, enormous quantities of ancient Martian water may now be imprisoned inside the crust. Invisible, immovable, hidden beneath billions of tons of stone. This possibility changes how scientists think about Mars' history. Instead of asking only where the water escaped, they now ask how much still remains beneath the surface. That question has become increasingly important because every new mission seems to uncover another clue. The European Space Agency's Mars Express spacecraft detected enormous deposits of water ice buried below the surface. NASA's Mars Reconnaissance Orbiter found evidence for glaciers concealed beneath layers of dust and rock. Polar ice caps contain additional reserves frozen into layered sheets that record changes in climate stretching back millions of years. Mars still possesses water, just not where it once existed, and certainly not in forms capable of sustaining rivers today. Yet water alone isn't enough to tell the full story. Climate also depends on atmosphere. Earth remains warm largely because greenhouse gases trap part of the sun's heat. Carbon dioxide, methane, and water vapor absorb infrared radiation that would otherwise escape back into space. Mars still has carbon dioxide. In fact, it makes up about 95% of the current atmosphere. So why isn't Mars warm? Because percentages can be misleading. Although carbon dioxide dominates the Martian atmosphere, the atmosphere itself is incredibly thin. The total amount of greenhouse gas surrounding Mars is only a tiny fraction of Earth's atmospheric mass. There simply isn't enough of it to retain much heat. As a result, temperatures swing dramatically. Near the equator on a sunny afternoon, conditions can briefly become surprisingly mild. But after sunset, temperatures plunge rapidly because almost no atmosphere exists to trap warmth. The same world can experience comfortable daytime conditions, followed by nights colder than Antarctica. It is a planet of extremes. And those extremes continue producing phenomena unlike anything on Earth. Dust storms. Some begin as local whirlwinds, dancing across empty plains. Others grow into continent-sized weather systems. Occasionally, they expand until the entire planet disappears beneath a swirling blanket of reddish dust visible, even through amateur telescopes on Earth. Imagine standing on Mars during one of these global storms. The sun slowly fades. The sky darkens into shades of copper and brown. Fine dust fills the atmosphere for weeks or even months. Visibility drops dramatically. Solar-powered spacecraft struggle to generate electricity. The landscape vanishes behind an endless haze. One such storm ultimately ended NASA's Opportunity rover mission after nearly 15 extraordinary years exploring the Martian surface. Dust blocked sunlight from reaching its solar panels. Engineers waited, hoping clearer skies would allow the rover to recharge. The call never came. Opportunity fell silent forever. Its final chapter became one of the most emotional moments in space exploration, reminding humanity that Mars remains an unforgiving world despite decades of technological progress. But even its dust storms tell scientists something remarkable. They reveal an atmosphere still active enough to transport enormous quantities of material across the planet. Sand dunes migrate. Dust settles in new patterns. Fresh impacts expose darker material beneath bright surfaces. Mars is not geologically dead. It is quieter than Earth, but it is still changing. Then came another surprise. Researchers examining high-resolution orbital images noticed dark streaks appearing seasonally on steep crater walls. These features, called recurring slope lineae, seemed to grow during warmer months before fading again. The discovery ignited worldwide excitement. Could liquid water still exist on modern Mars? For years, scientists debated whether salty brines might briefly flow across the surface. Certain salts can lower water's freezing point significantly, allowing liquids to remain stable under conditions that would normally produce ice. If true, these streaks could represent modern liquid water. But newer evidence has challenged that interpretation. Many researchers now believe the streaks result from dry flows of dust and sand rather than liquid. Once again, Mars refused to provide easy answers. Every discovery opened another mystery. Every solution created fresh questions. That pattern has become almost characteristic of planetary science. The better we understand Mars, the stranger it becomes. Perhaps no mystery illustrates this better than methane. Methane is an intriguing gas because, on Earth, much of it is produced by living organisms. Microbes buried beneath wetlands, animals digesting food, and decaying organic matter all release methane into the atmosphere. Of course, geology can produce methane too. Certain chemical reactions involving water and specific rocks generate methane without biology playing any role. So when telescopes and spacecraft detected traces of methane on Mars, scientists immediately faced an extraordinary puzzle. Where was it coming from? Even more puzzling, why did it seem to appear and disappear? NASA's Curiosity rover occasionally measured sudden spikes in methane concentration near the surface. Then, just as mysteriously, the gas seemed to fade away. Orbital instruments often struggled to confirm those measurements consistently. Some observations matched. Others did not. No single explanation satisfies all the available evidence. Perhaps methane seeps upward through underground fractures before ultraviolet sunlight destroys it. Perhaps unknown chemical reactions remove it faster than expected. Perhaps localized geological activity releases tiny bursts from deep below. Or perhaps the measurements themselves reflect complexities scientists are still learning to understand. Whatever the answer, methane has kept one extraordinary possibility alive. If underground environments still contain liquid water, heat, and chemical energy, could microscopic life survive there today? No credible evidence has yet confirmed life on Mars. None. But neither has science completely ruled it out. Deep beneath the frozen surface, shielded from intense radiation, pockets of briny water may still exist. On Earth, microbes thrive in places once considered completely uninhabitable, inside Antarctic ice, beneath the ocean floor, around volcanic vents, and kilometers below ground. Life has repeatedly surprised us, which is precisely why Mars continues attracting mission after mission. Because solving the mystery of Mars isn't only about understanding another planet. It may ultimately answer one of humanity's oldest questions. How common is life in the universe? And just as scientists were beginning to piece together Mars' environmental collapse, a discovery buried deep within the planet's ancient crust hinted that the greatest clue had been there all along. The oldest landscapes on Mars are unlike anything else in the solar system. They are battered, fractured, and scarred by countless impacts, preserving a record that Earth erased long ago. Our own planet constantly renews its surface through plate tectonics, erosion, oceans, and weather. Mars, by contrast, became a time capsule. It froze much of its earliest history in place, allowing scientists to read events that happened more than 4 billion years ago. Those ancient rocks hold a remarkable secret. When orbiters began mapping the planet in extraordinary detail, researchers noticed something almost impossible to explain. Certain regions of Mars still possessed magnetic signatures, not a global magnetic field like Earth's, but isolated patches locked inside the crust itself. It was as if pieces of the planet remembered something the rest had forgotten. These magnetic minerals could only have formed while Mars still possessed a powerful global magnetic field. As molten rock cooled billions of years ago, tiny iron-bearing crystals aligned themselves with the planet's magnetic field, preserving its direction like microscopic compass needles frozen in time. The rocks became geological hard drives. Even after the magnetic field disappeared, the memory remained. By measuring these ancient magnetic patterns, scientists concluded that Mars once generated a magnetic shield surprisingly similar to Earth's. It wasn't weak. It wasn't temporary. It was a fully functioning planetary defense system. Then somehow it died. The disappearance of that magnetic field marks one of the greatest turning points in Martian history. But another mystery emerged. When exactly did it happen? And more importantly, why? One possibility points deep beneath the surface. Unlike Earth, whose interior remains incredibly active, Mars appears to have cooled much faster. Its smaller size meant it lost internal heat more efficiently. Eventually, the molten outer core may have cooled enough that the vigorous convection responsible for powering the magnetic dynamo slowed to a halt. Without flowing liquid metal, no dynamo. Without a dynamo, no magnetic field. Without a magnetic field, no protection from the sun. It's a simple chain of events. Perhaps too simple, because several observations refuse to fit neatly into that explanation. Some scientists suspect Mars suffered an event so catastrophic that it fundamentally altered the planet's interior. The evidence lies not in the atmosphere, not in the rivers, but in the planet's shape itself. If you compare Mars carefully with Earth, something seems strangely unbalanced. The northern hemisphere is remarkably smooth and relatively low in elevation. The southern hemisphere is older, rougher, thicker, and heavily cratered. The difference is extraordinary. Planetary scientists call it the Martian dichotomy. Nearly 1/3 of the planet sits noticeably lower than the rest. No other rocky planet displays such a dramatic contrast across an entire hemisphere. So what created it? One explanation suggests internal geological processes stretched and thinned the northern crust billions of years ago. Another is far more dramatic. A colossal impact. Not just an asteroid. Something almost unimaginably large. According to the giant impact hypothesis for Mars, an object roughly the size of Pluto may have collided with the young planet during the earliest days of the solar system. The collision would have released energy beyond comprehension, melting enormous portions of the crust, reshaping an entire hemisphere, and potentially explaining the planet's unusual topography. If correct, it would rank among the largest impacts ever experienced by any terrestrial planet. Computer simulations have shown that such an event could indeed produce the northern lowlands remarkably similar to what we observe today. But the implications don't stop there. A collision of that scale might also have disrupted the planet's interior. It may have altered heat flow inside Mars. It may have affected the core. Some researchers even wonder whether it contributed to weakening the magnetic dynamo itself. The evidence remains incomplete. No scientific consensus exists. Yet the possibility lingers, because Mars continues revealing clues that refuse to disappear. Then there are the moons. Phobos and Deimos. Small, dark, misshapen. Unlike Earth's large, spherical moon, these tiny satellites resemble captured asteroids. At least, that's what scientists once believed. Their irregular shapes certainly support the idea. But they're nearly circular. Equatorial orbits tell a different story. Captured asteroids usually end up following highly elliptical, tilted paths. Phobos and Deimos do not. Recent research has revived another possibility. Perhaps both moons formed from debris blasted into orbit after that same giant impact. If Mars truly experienced a collision powerful enough to reshape half the planet, enormous quantities of molten rock would have been thrown into space. Over time, that debris could have merged into small moons. The idea is still debated. Future sample return missions from Phobos may finally settle the question. If the moon's composition closely matches Martian crust, the impact theory gains powerful support. If not, another mystery awaits. Mars seems determined never to provide simple answers. Even its weather tells stories written across geological time. Today, the atmosphere is so thin that liquid water cannot remain stable for long. Yet seasonal changes still occur. Carbon dioxide freezes directly out of the atmosphere during winter, forming enormous polar caps of dry ice. When spring returns, sunlight causes the frozen carbon dioxide to sublimate, changing directly from solid into gas. This process creates strange geyser-like eruptions beneath translucent ice layers. Jets of gas burst upward through weak spots, carrying dark dust with them before settling back across the surface. From orbit, these eruptions leave branching patterns resembling giant black spiders crawling across the polar regions. They are known simply as spiders. No animals. No life. Just physics creating one of the strangest natural landscapes in the solar system. Elsewhere, dust devils dance silently across endless plains. Unlike Earth's tornadoes, they often form under crystal-clear skies. Some stretch several kilometers into the atmosphere, while slowly wandering across the landscape. Ironically, these whirlwinds have occasionally cleaned dust from the solar panels of Mars rovers, unexpectedly extending their missions. Even the planet's harshest conditions sometimes work in humanity's favor. But perhaps the greatest breakthrough came not from weather, nor volcanoes, nor impacts. It came from chemistry. In 2011, NASA announced a discovery that fundamentally changed how scientists viewed ancient Mars. Curiosity had not yet landed. Perseverance was still years away. Yet orbital instruments had already identified widespread clay minerals, sulfates, and other water-altered rocks. These minerals weren't randomly scattered. Different minerals appeared in different geological eras. That pattern allowed scientists to reconstruct an environmental timeline stretching billions of years into the past. Early Mars appears to have been relatively neutral in pH, rich in liquid water, and potentially suitable for microbial life. Later, volcanic activity and atmospheric loss altered surface chemistry. Water became increasingly acidic in many regions. Eventually, as the atmosphere continued thinning, stable surface water largely disappeared altogether. Mars didn't simply dry out. It evolved through multiple distinct environmental stages. Some lasted hundreds of millions of years. Others may have unfolded surprisingly quickly. That realization transformed the search for ancient life. Instead of asking whether Mars was ever habitable, scientists began asking when and where. Different environments existed at different times. Ancient lakebeds, hydrothermal systems, river deltas, underground aquifers. Each represents a unique opportunity for biology, if biology ever emerged. That's precisely why NASA selected Jezero Crater as Perseverance's landing site. Billions of years ago, a river emptied into a large lake there, depositing sediments exactly as rivers do on Earth. Those sediments are exceptional at preserving evidence. On our own planet, ancient microbial fossils are often found within similar environments. If Mars ever hosted microscopic life, Jezero became one of the best places to search. Since landing in 2021, Perseverance has been collecting carefully selected rock cores, unlike anything previously gathered on another planet. Each sample is sealed inside specially designed tubes. They are not being analyzed completely on Mars. Instead, they are waiting for humanity to bring them home. Because laboratories on Earth possess instruments far more powerful than anything we can currently send across millions of kilometers of space. Those tiny cylinders may one day answer questions scientists have debated for generations. Or they may deepen the mystery even further. History suggests Mars prefers the second option. Every mission has followed the same pattern. Expectation, discovery, confusion, then an entirely new question. The Viking landers searched directly for life in the 1970s. Their results remain controversial. Spirit and Opportunity revealed overwhelming evidence of ancient water. Curiosity confirmed long-lasting habitable environments. Perseverance is preserving pieces of Mars itself for future generations to examine. Each mission solved part of the puzzle. None completed it. Because the greatest mystery surrounding the murder of Mars may not be how the planet died. It may be whether something survived the catastrophe. Hidden beneath kilometers of ancient rock, beyond the reach of deadly radiation, there could still exist environments untouched for billions of years. Dark, warm, chemically active, and perhaps not as lifeless as the silent surface above would have us believe. The deeper scientists looked beneath the surface of Mars, the more the planet resisted the label of dead. Its deserts appeared frozen in time, yet beneath that dusty exterior, evidence suggested a world that might still possess energy, movement, and perhaps even reservoirs of liquid water hidden far below. If the surface tells the story of a victim, the underground may still be guarding the final witness. One of the biggest challenges in exploring Mars is that we have barely scratched its surface. Every rover ever sent has examined only a microscopic fraction of the planet. Even the deepest drill has reached just a few centimeters into the ground. Compared to Earth's mines, which descend several kilometers, humanity has barely disturbed the Martian skin. That limitation matters. Cosmic radiation constantly bombards the Martian surface. Without a thick atmosphere or a global magnetic field, high-energy particles from space penetrate directly into the soil. Over millions of years, this radiation destroys many complex organic molecules that might otherwise survive. Any evidence of ancient life near the surface has been exposed to this relentless assault for billions of years. But go just a few meters underground, and the story changes. Rock is an excellent shield. Beneath layers of sediment, radiation drops dramatically. Temperatures become more stable. Water ice can persist for immense periods, and in some regions, pressure may even allow pockets of salty liquid water to exist. That possibility has fascinated scientists for decades. On Earth, life occupies environments once thought impossible. Microorganisms live more than 3 kilometers beneath the surface, inside solid rock. Others survive beneath Antarctic glaciers, isolated from sunlight for hundreds of thousands of years. Entire ecosystems flourish around hydrothermal vents on the ocean floor, where sunlight has never reached. These discoveries changed biology forever. Life does not necessarily need sunlight. It needs energy. Chemical reactions between water and rock can provide that energy. If similar reactions continue deep inside Mars, then the planet could still possess habitable environments even today. No mission has confirmed this, but no mission has ruled it out either. One of the strongest pieces of evidence arrived unexpectedly in 2018. Using data from the European Space Agency's Mars Express spacecraft, researchers reported signs consistent with a lake of liquid water buried beneath the South Polar ice cap. Radar signals reflected from beneath the ice in a way that resembled subglacial lakes found beneath Antarctica. The announcement generated enormous excitement. A lake beneath Mars. Liquid water. Present day. If correct, it would represent one of the most significant discoveries in planetary science. Yet, as often happens with Mars, certainty proved elusive. Other scientists questioned whether the radar reflections truly indicated water. Alternative explanations suggested unusual clay deposits or highly conductive minerals could produce similar signals. Additional observations continue, but no definitive answer has emerged. The mystery remains alive. Even uncertainty tells us something important. Mars is far more complex than a frozen ball of rock drifting through space. It continues to challenge our assumptions. Another mystery emerged from earthquakes. For decades, scientists knew surprisingly little about the Martian interior. Everything changed in 2018 when NASA's InSight lander touched down on Elysium Planitia, carrying one of the most sensitive seismometers ever placed on another planet. Its mission was simple in concept. Listen. For the first time in history, humanity waited to hear the heartbeat of another world. At first, silence dominated. Then, the planet began to tremble. InSight detected hundreds of Marsquawks. Some were gentle vibrations, barely distinguishable from background noise. Others were powerful enough to ripple through the crust and mantle. Each quake carried information about the planet's hidden interior. By studying how seismic waves traveled through Mars, scientists reconstructed its internal structure, much like doctors use ultrasound to examine the human body. The results were remarkable. Mars possesses a crust, a mantle, and a large metallic core. But the core turned out to be larger and less dense than many models had predicted. Instead of consisting mostly of iron and nickel, it appears to contain significant amounts of lighter elements such as sulfur, oxygen, carbon, and hydrogen. Those elements influence how the core behaves. They affect melting temperatures. They influence convection. They shape the history of the magnetic dynamo. Each new measurement refined the timeline of Mars' transformation. The planet had once been geologically vigorous. Volcanoes erupted. Its magnetic field operated. Water flowed. Then internal activity gradually declined. The core no longer generated a global magnetic shield. The atmosphere thinned. Surface water vanished. The climate collapsed. But InSight revealed something else. Mars still isn't completely inactive. The planet continues to experience seismic activity today. It continues to release heat from its interior. It continues evolving, albeit far more slowly than Earth. Even now, billions of years after its greatest transformation, Mars refuses to become entirely still. Meanwhile, orbiters searching the surface noticed fresh impact craters appearing between successive photographs. That alone wasn't surprising. Asteroids continue striking planets throughout the solar system. What surprised researchers was what those impacts exposed. Bright patches of ice. In several locations, newly formed craters blasted through the dusty surface, revealing brilliant white deposits beneath. Over time, those patches slowly faded as the exposed ice sublimated into the atmosphere. The implication was extraordinary. Large quantities of frozen water lie just beneath the surface across many regions of Mars. Future astronauts may not need to transport all their water from Earth. Instead, They could extract it directly from Martian soil. Water means drinking supplies. It means breathable oxygen through electrolysis. It means hydrogen fuel. It means agriculture. Every discovery of buried ice strengthens the possibility that humans could one day establish a permanent presence on Mars. Yet reaching the planet is only the beginning. Surviving there presents an entirely different challenge. A typical day on Mars lasts just over 24.5 hours, remarkably similar to Earth's rotation. But almost everything else is different. The air is unbreathable. Average temperatures hover around -63 degrees Celsius. Radiation levels greatly exceed those experienced on Earth's surface. Dust infiltrates machinery, seals, and instruments. The reduced gravity, only about 38% of Earth's, may produce long-term health effects that remain poorly understood. Mars is close enough to inspire dreams, far enough to punish mistakes. Despite those dangers, space agencies around the world continue preparing for the next era of exploration. NASA, the European Space Agency, the China National Space Administration, and other organizations are developing technologies that could eventually place humans on the Martian surface. Private companies have accelerated those ambitions even further. For the first time in history, the question is shifting from can humans reach Mars to how should we live there? But another mission may prove even more important than sending people. Bringing Mars home. The Mars Sample Return Campaign aims to deliver carefully selected rock samples collected by Perseverance back to Earth. The mission is extraordinarily ambitious. A lander must arrive safely. A small rocket must launch from another planet, the first time in history this has ever been attempted. The sample container must rendezvous with an orbiter in Martian orbit. Then the spacecraft must travel millions of kilometers back to Earth before releasing the samples for secure recovery. Each step represents an engineering challenge, unlike anything attempted before. Yet scientists believe the reward justifies the effort. Those rocks preserve a record stretching back nearly 4 billion years. Inside them may lie chemical signatures revealing exactly when water disappeared. They may contain evidence of ancient volcanic activity. They may reveal details of Mars' changing atmosphere. And perhaps, just perhaps, they may contain the first convincing evidence that life once emerged beyond Earth. Not intelligent life. Not civilizations. Not canals stretching across deserts. Something far more profound. Simple microbial organisms. If such evidence exists, it would forever change humanity's understanding of its place in the universe. Life would no longer be unique to Earth. It would demonstrate that biology can emerge independently on different worlds when conditions allow. That realization would reshape astronomy, biology, philosophy, and perhaps even our understanding of ourselves. But science demands extraordinary evidence for extraordinary claims. Every sample will undergo years of meticulous analysis. Every result will be challenged. Every alternative explanation will be tested. Because the stakes could not be higher. The mystery of Mars has already rewritten textbooks countless times. It deserves nothing less than absolute certainty. And as researchers continue piecing together billions of years of planetary history, one realization becomes increasingly difficult to ignore. Mars was not merely unlucky. It was a world that stood at the edge of habitability, balanced between becoming another living planet or becoming the silent desert that circles the sun today. The difference may have depended on a handful of events that unfolded billions of years before humanity ever existed to witness them. And understanding those events may ultimately reveal something even more important than the fate of Mars. It may explain why Earth is still alive. For billions of years, Mars has circled the sun in almost complete silence. No oceans crash against its shores. No forests sway beneath its skis. No rain falls across its valleys. Yet every orbit carries the memory of a world that was once dramatically different. The red planet isn't simply a frozen desert. It is a planetary archive, preserving one of the greatest transformation stories in the solar system. And after decades of exploration, scientists have reached a remarkable conclusion. Mars was not born dead. It became dead. That distinction changes everything. When the first robotic explorers landed on Mars in the 1970s, they encountered what appeared to be a barren, inactive world. The landscape looked timeless, almost untouched. It was easy to assume that Mars had always been cold, dry, and lifeless. Today, that picture has been completely overturned. Evidence collected by orbiters, landers, and rovers has revealed an ancient world with rivers that flowed for hundreds of kilometers, lakes that persisted for immense spans of time, groundwater that altered entire landscapes, and volcanic activity powerful enough to reshape continents. Layer by layer, scientists reconstructed a history that no telescope from Earth could ever have uncovered. Mars wasn't merely another rocky planet. It was a world with potential, perhaps even with opportunity. Whether life ever took advantage of that opportunity remains unanswered. And that unanswered question may be the greatest scientific mystery of all. If microscopic organisms appeared on Mars during its warm, wet youth, they would have emerged completely independently from life on Earth, unless rocks blasted between the two planets carried microbes across space, a possibility scientists call lithopanspermia. We know that large asteroid impacts can eject pieces of planetary crust into space. We have discovered Martian meteorites here on Earth, proving that rocks can travel naturally from Mars to our planet. That means tiny fragments of Mars have been sitting in laboratories for decades. Scientists have carefully examined these meteorites, searching for signs of ancient biology. Some have contained intriguing mineral structures and organic compounds, but none has provided convincing proof of life. Every exciting claim has eventually faced alternative geological explanations. That is how science works. Extraordinary conclusions survive only after every ordinary explanation has failed. Mars continues to pass that test. It continues to refuse simple answers. One reason is that organic molecules alone do not prove biology. Carbon-based compounds form throughout the universe. They exist inside comets. They exist within interstellar clouds. They have been detected on asteroids. NASA's Curiosity Rover confirmed the presence of preserved organic molecules inside ancient Martian rocks, an important discovery because radiation gradually destroys these compounds near the surface. But organic chemistry is not the same as life. The ingredients for bread are not bread. The ingredients for life are not life. Still, every discovery narrows the search. Scientists now know where ancient lakes existed. They know where river deltas deposited fine sediments capable of preserving microscopic fossils. They know which rocks formed in long-lasting water. They know where future explorers should look. The mystery has become more focused than ever before. At the same time, Mars has become something even more valuable. A warning. Earth and Mars began their histories with surprising similarities. Both formed from the same protoplanetary disk, roughly 4.5 billion years ago. Both possessed volcanic activity. Both experienced asteroid bombardment. Both contained water. Both may once have had thick atmospheres. Yet today, they could hardly appear more different. Earth remains vibrant. Its magnetic field still shields the atmosphere. Plate tectonics continuously recycle nutrients and reshape continents. Its climate, though constantly changing, continues supporting an astonishing diversity of life. Mars followed another path. Its smaller size allowed internal heat to escape more rapidly. Its magnetic dynamo shut down. Its atmosphere gradually eroded. Surface water disappeared. Habitability faded. The comparison reminds us that planetary evolution is not guaranteed to produce living worlds forever. Habitability can be temporary. Scientists studying exoplanets, worlds orbiting distant stars, often classify planets as either habitable or uninhabitable. Mars reminds us that reality is far more dynamic. A planet can move between those categories over geological time. Understanding exactly why Mars changed helps researchers recognize which distant planets might remain stable long enough for life to emerge and evolve. In that sense, Mars has become one of astronomy's greatest teachers. It teaches us how planets grow old. It teaches us how atmospheres disappear. It teaches us how magnetic fields protect worlds. And perhaps most importantly, it teaches us to appreciate how extraordinary Earth truly is. Our planet's magnetic field is constantly changing, but it has never disappeared completely. Its molten outer core continues generating the invisible shield that protects our atmosphere from the solar wind. Without that protection, Earth's future might have looked very different. The oceans may not have survived in their present form. The atmosphere could have slowly thinned. Complex life may never have evolved. Every aurora dancing above Earth's polar skis is a visible reminder that our magnetic shield is still standing. Those beautiful curtains of light represent particles diverted away from the atmosphere. On Mars, similar particles struck directly. The contrast is breathtaking. Yet Mars is not merely a relic of the past. It is also humanity's future laboratory. Within the coming decades, astronauts may stand where only robots have traveled. They will walk through dried riverbeds that last carried water billions of years before the first humans existed. They will climb hills first photographed by distant orbiters. They will collect rocks with their own hands and explore caves that may have remained sealed since the earliest chapter of solar system history. Those caves are attracting increasing scientific interest. Volcanic regions on Mars contain enormous lava tubes, natural tunnels formed as flowing lava cooled on the outside, while molten rock continued moving beneath. Some may be hundreds of meters wide and extend for many kilometers. Inside these underground caverns, temperatures remain more stable. Radiation levels drop dramatically. Future astronauts could use them as natural shelters. More intriguingly, if microbial life ever retreated underground as surface conditions deteriorated, lava tubes might preserve evidence that the open landscape no longer can. One day, explorers may shine lights into places that have remained in complete darkness for billions of years. The first footprint inside one of those caves could become one of the defining moments in the history of exploration. Perhaps nothing will be there except rock. Perhaps something else has been waiting. Until that moment arrives, Mars continues speaking through machines. Every photograph sent across millions of kilometers expands humanity's understanding. Every seismic vibration recorded by InSight reveals another layer of the interior. Every atmospheric measurement made by MAVEN refines models of planetary evolution. Every rock sample collected by Perseverance preserves another page from a story written 4 billion years ago. The remarkable part is that these missions were never designed simply to answer questions. The greatest missions create better questions. Mars has done exactly that. It forced scientists to abandon the belief that small rocky planets remain unchanged forever. It challenged assumptions about climate evolution. It reshaped the search for extraterrestrial life. It transformed how we evaluate potentially habitable worlds around distant stars. And it reminded us that the universe is often far more creative than our theories. So was Mars really murdered? In a literal sense, no. No cosmic assassin arrived to destroy a thriving world. The title is a metaphor for one of the most dramatic natural transformations known in planetary science. The murder was carried out by time, physics, and the unforgiving environment of space. A cooling interior silenced the magnetic dynamo. The loss of that invisible shield exposed the atmosphere to the solar wind. Over immense spans of time, Gases escaped into space. Surface pressure fell. Liquid water became unstable. The climate crossed a threshold from which it could not recover. The victim was not simply a planet. The victim was possibility. The possibility that Mars could have remained warm. The possibility that rivers might still flow today. The possibility that life, if it ever began, might have continued evolving for billions of years. Yet even that conclusion remains incomplete. Science is built on evidence, not certainty without proof. There are still unanswered questions about the exact timing of atmospheric loss, the role of giant impacts, the persistence of underground water, and the chemistry responsible for methane detections. Future missions, and eventually returned samples, may refine or even revise parts of the story. That is not a weakness of science. It is its greatest strength. Every new discovery replaces assumption with evidence. Every mission sharpens humanity's understanding of the cosmos. Every answer opens another door. Somewhere beneath the dust of Mars, rocks still preserve memories older than any surviving landscape on Earth. They have waited nearly 4 billion years for someone capable of reading them. For the first time in history, that someone is us. The greatest mystery in space was never just about the death of a planet. It was about understanding how worlds change, how life may begin, how fragile habitability can be, and why our own blue planet remains one of the rarest and most precious places we have ever known. The next time you look toward the red light crossing the night sky, remember that you are not looking at a failed world. You are looking at a chapter of our own story. Because by uncovering the truth about Mars, humanity is slowly uncovering the truth about Earth, about life, and about our place in an ever-expanding universe. If this journey through the murder of Mars, the greatest mystery in space, sparked your curiosity, like, share, and subscribe to Starsky Science for more cinematic science documentaries that explore the greatest mysteries of the universe.